In this video, we are going to discuss different types of thermal processes. Now, when we do a thermal process, we're going to hold a certain variable constant, so a certain state variable like pressure, temperature, volume constant. And this is going to be forced. This isn't something that naturally occurs. When we hold the volume constant and change the pressure and temperature of the gas, if the gas was just free floating, the volume would change as well as the pressure and the temperature. So we're forcing something to have the same volume. And we're going to discuss the implications for the process of holding that one particular variable constant. So we're going to start here by discussing isobaric. During an isobaric process, the pressure is held constant. And you can remember this because the unit of bar is a unit of pressure. And you would have learned about the unit of bar when you did Lab 304 because you had to convert from bar into pascals. I'm now going to refer you over to the table I have over here in the corner. So in this first column we have the different type of processes, and up top we have the different process variables that make up the first law of thermodynamics. So column 1 is going to tell you how to calculate the change in internal energy for each type of process. And we learned about that in the video for the first law of thermodynamics. So this equation we're all aware of. We'll talk about why isothermal is 0 in a little bit later. Now when we do isobaric and go how to calculate the heat using your state variables, we need to discuss a new term. Heat in an isobaric process is going to equal the number of moles times the molar specific heat at constant pressure times the change in temperature. And remember, change in temperature means to take temperature final minus temperature initial. And once again, because it's a change in temperature, it either both has to be Celsius or both has to be Kelvin. So let's talk about what molar specific heat is. Now we're finding our specific heats while holding pressure constant. Molar specific heat and constant pressure is going to equal 5/2 times the ideal gas constant for monatomic and 7/2 times R for diatomic. And we get this from the fact that the molar specific heat at constant pressure is equal to the molar specific heat at constant volume plus the ideal gas constant. Last, we need to talk about how to calculate work for an isobaric process. So we go isobaric, we go work, and we already know how to calculate work using the negative of the pressure times the change in volume. But you can also use the ideal gas law to make a substitution and say that work is equal to the negative of the number of moles times the ideal gas constant times the change in temperature. So this is an either-or situation. You can calculate work for isobaric using this relationship or this relationship. Alright, so now I want to introduce a pressure versus volume graph. We are going to plot pressure, and we're going to do it in pascals versus volume in meters cubed. And as we go from the initial state to the final state, we will monitor what happens to the pressure and the volume. So for isobaric, since the pressure is going to be the same between stage A and stage B, so between A and B, we would have a horizontal line because the y is staying constant while the x term is changing still. So for a isobaric process, the line of your data points would make for a pressure versus volume graph is a horizontal line. The next process we are going to discuss is an adiabatic process. Now, an adiabatic process is kind of strange because it occurs when an expansion happens so quickly that there isn't time for energy, or specifically thermal energy, to be exchanged between the system and the environment. Which means during this process, Q is going to equal 0. So any change in internal energy, because if we look at our first law of thermodynamics, if we plug a 0 in here, our change in internal energy is going to equal work. If we go up to our table up in the corner for adiabatic, for change in internal energy, we're going to use the same relationship as before. This means that during an adiabatic process, the temperature can change still. We're just going to do it through a change in volume rather than an actual exchange of thermal energy. Q is going to be 0, as we discussed over here, and then you're going to use essentially the first law of thermodynamics to find the work done by monitoring what the change in internal energy is based upon the change in temperature. Now let's look at our pressure versus volume graph. Alright, so we're going to draw our two axes here. So we have pressure in pascals and volume in meters cubed. And we're going to get a line that's not horizontal, that's not linear, that's not vertical, but is curved. And it's looked very similar to the line that you got when you did the Boyle's Law experiment. But it's not quite the same. Now you guys would have done a line of best fit and gotten y equals some constant x to hopefully the -1 power. This graph though, this term is going to be different. It's not going to be to the -1 power. It's going to be y equals some constant x to the negative gamma. And gamma here is not really gamma. It's gamma because it's a Greek letter. But it stands for the adiabatic index. And the adiabatic index is the ratio of the molar specific heat at constant pressure to the molar specific heat at constant volume. Now if we take the relationship we have over on the side here, and we sub in the actual variables, y was pressure, this is going to still be some constant that we don't care about, volume to the negative gamma. Now I want to rearrange a little bit. The first thing I'm going to do is take pressure equals that constant and rewrite it as volume to the positive adiabatic index. A negative exponent multiplied is the same thing as divided by a positive exponent. And then I'm going to multiply the pressure times the volume raised to the adiabatic index, and that's going to equal a constant. So that no matter what pressure volume I pair, if I pick this pressure volume pair, or this pressure volume pair, or this pressure volume pair, it's always going to be, when I use my relationship here, so if I take that pressure times volume to the adiabatic index, it's always going to equal the same constant. And that allows me to set one state equal to another state. So I can say that pressure 1 times volume 1 raised to the adiabatic index, and only the volume is raised to the adiabatic index, is equal to pressure 2 times volume 2 raised to the adiabatic index. So if you have an adiabatic process and you know something about the initial pressure and volume, you can either use this relationship to find either the pressure or the volume at another point in the change of the gas, depending upon what you're given in the problem. But this relationship here only applies to an adiabatic process. And how you know that is it contains the adiabatic index. The next thermal process we are going to discuss is isovolumetric. And as the name implies, because iso means the same, is the same volume. So this means that during the process, the volume is held constant. So if we look at the first law of thermodynamics, and we learn that work is pressure times the change in volume. Since volume is constant, that means that the change in volume is equal to 0. Or in other words, work is going to end up equaling 0 during isovolumetric process, so that your change in internal energy is due only to heat, or the change in thermal energy. That means that if we look up here at our table for isovolumetric, the first column is how you calculate the change in internal energy. That's the same formula we've always used. And to calculate the heat, we're using our first law of thermodynamics. And then, as we said before, work is going to be 0. Let's look at a pressure versus volume graph for this. So we're going to do pressure versus volume, so pressure in pascals, volume in meters cubed. And for this case, because our volume is held constant, or our x value is held constant, but our y value, or pressure, is still changing, we're going to get a line that is vertical. Our next thermal process is going to be isothermal. In an isothermal process, the temperature is going to be held constant. And looking at our change in internal energy formula, since our temperature is held constant, the change in temperature is going to be 0, which means our change in internal energy is going to equal 0. So if we have our first law of thermodynamics here, this term is 0, we are going to get that work equals a negative heat. So what goes in must come out. If you add energy through the system by doing mechanical work, it has to leave the system through heat, or a negative change in thermal energy, or vice versa. If you add energy through heat, then you're going to get a negative work to expel that energy again. All right, so I'm going to add the table in. So let's look at the table again. So for isothermal, we said that the change in internal energy is going to be 0. We're going to calculate the heat using this relationship here from the first law of thermodynamics. And we're going to be able to calculate work using this relationship here, where work is going to equal the negative of the number of moles times the ideal gas constant times temperature. This temperature must be in Kelvin because it's not a change in temperature, times the natural log. So you're going to need to find the natural log button on your calculator of the final volume divided by the initial volume. I'm not going to show you guys where this equation comes from because it does involve taking an integral of a function. Alright, so now let's look at our pressure versus volume graph. So pressure in pascals and volume in meters cubed. And our line here is going to look very familiar. It almost looks like the adiabatic one. In fact, it should look like the graph that you got from the Boyle's Law part of Lab 304, where you plotted pressure in the y-axis, you got some constant x to the -1. So pressure is going to equal some constant times volume raised to the -1 power. So pressure and volume are inversely related to each other. And keep in mind this constant I keep ignoring here in cases things like the number of moles, the temperature of the gas. So it's a constant, but we do know what it is. We just are more worried about what is changing, which is the pressure and the volume. The last type of process we're going to discuss is a general process. And this is a process where nothing is held constant. All right, so let's add back in our table. So notice here in the general case, once again, we're still calculating the change in internal energy the same way. We're using the first law of thermodynamics to find the heat. So we need to talk about the work. And work is going to be based upon a pressure versus volume graph. So let's set up a pressure versus volume graph. Alright, so we have pressure here, and then volume on our x-axis. And the way we're going to find the work here is by using the area under the line, or the area underneath the curve. So work here is going to equal area. So if my process looks like this, which is none of the ones we discussed before, because it's not a horizontal line, it's not a vertical line, it's not a curved line like it's inversely related to each other, it's a straight line. So we're going to find the area underneath that line. So the first thing I'm going to do is draw two vertical lines down to find exactly what my area is. And I encourage you to do this because otherwise you may add this area in, or this area in, or this area in. And remember, it's always under, not over, under. Alright, so this is the area we need to know. Now this is a pretty strange shape, so I'm actually going to split it into two shapes in order to be able to do this one. And so I'm going to draw a line across here. I'm going to call this area 1 and area 2. So area 1 is the area of a triangle, and area 2 is the area of a rectangle. I'm now going to use my given pressure and volume values to define the sides of the triangle. So here we're going to have P1, V1, and here we're going to have P2 and V2 as my XY pair. So, and keep in mind I wrote these down backwards. This is your Y term, this is your X term, this is your Y term, this is your X term. So we're going to do 1/2 times the base of the triangle. So the base of the triangle is going to be this here. So we're going between our volume 2 and our volume 1. And I'm always going to do my subtraction so I get a positive number. And then the height of the triangle here is going to be this side here. So that's going to be defined by P2 and P1. But this time I'm going to subtract P1 minus P2. So once again, I'm doing a positive subtraction because P1 is going to be bigger than P2. So that takes care of the triangle. Now I need to add the rectangle. So I'm going to do the length. So I'm going to say this is length, and once again that's defined as volume. So I'm going to do volume 2 minus volume 1. And then we're going to do the width of the rectangle. So that's going to be this side here. And this is always the trickiest one, because here this point is P2, and then down here this point is actually 0. So we're going to do P2 minus 0. Then I would plug in my values in order to actually calculate the work. And then you have to decide whether or not it is positive or negative. And this is where the sign rules that I introduced at the beginning of this topic come in. If you have compression where the volume is decreasing, it's going to end up being positive work. And if you have expansion where the volume is increasing, it's going to be negative work. So I would have to tell you in the problem, are you going from here to here? So you're going up like this, which would be compression, or are you going down this way, which is expansion? And I would do that by putting an arrow. So if I said put a little arrow like this down, you would know you're going from a small V1 to a bigger V2, and therefore its expansion and work would be negative. Now keep in mind this step here, so what your actual areas are, depends upon the line. I've done the most complicated one where you have to add together a triangle and a rectangle. But if I gave you a setup here where it's a horizontal line, we define our area underneath the curve. This area here would just be length times width. So you wouldn't need to add in the triangle. And when you did that, you would actually end up deriving the equation for the isobaric work. Or if I gave you a setup like this, where the line is vertical, there is no area under the curve. So in this case, area equals 0 and no work was done, and this matches up with what a volumetric graph would look like. Now I'm going to stick to standard geometric shapes, so I'm not going to make you find the area of a blob, so don't panic too much.